Alright, something a little different. Here you can see we have a toroid transformer. Now the windings of it are a 0.55mm laminated copper wire, and the winding with the green tape on it is our primary, and the winding going into this left hand side block is the secondary that is wound around with the primary, and that is a 1-to-1 wind ratio. You'll see here at the moment I've got this scope probe, the blue channel, which is channel 2, across the primary coil, and I have our red channel on our scope, channel 1, across the secondary that's wound with this primary. Now if we have a look, you will see, as I said, channel 2, which is behind the yellow one. If I turn that off you'll be able to see it. Channel 2 is showing us our Rms voltage across the primary, which is 1.24, and the yellow trace is across our secondary that's wound with that primary, and that's 1.28 volts. So very close to the same. We may have a little more, even though it's a 1-to-1 wind ratio, we may have a little more voltage due to the fact that we're running at 1 kHz. So the odd thing about this transformer is inside the core itself there is another coil that has the same amount of winds as the two outer coils. So the inner secondary and the outer secondary and the primary all are 1-to-1 turn ratios. So what I mean by having a inner secondary is we've cast a smaller toroid core, something like this ferrite one here, and we have put 70 odd turns around that of wire, and then we have encased that with the rest of the core material to make our complete core, so as we wrap the two outer windings on it. So there's actually a core in the middle of this completed core that has a secondary wound around it, which we are calling the inner secondary, and then, like I said, that is then encased with the same material that we built the inner core out of, and allowed to set. Then we wind the two outer windings on. The core material I'm using is this stuff here. It is cast iron powder, and I get this from work when we machine brake discs. I collect all the cast iron filings that come from that machining process. Very magnetic, and I simply use a 2-pack epoxy or a fiberglass resin, embedding resin, and make up a relatively dry mix just so it just sticks together. It is put into a mould, compressed, vacuum bagged, and then we end up with our core. This of course is just a ferrite core I'm using for an example, because I have no more made up at the moment, just the one we're looking at here. So yeah, we have a basically a separate transformer encased in the transformer core, and it has had some very interesting effects. So all 1-to-1 wind ratios as far as turns go, but of course the inner core, or our inner secondary, uses a lot less wire. Actually it uses half as much as we do on the outer secondary. So like I said, our blue channel is across our primary at the moment, and our red channel is across our outer secondary, and this one here that you see coming out of the centre of the core is our inner secondary winding. And remember, the turn ratio is exactly the same on all three windings. So we should get, that's our blue channel here, about 1.28 volts on our inner one, our inner secondary, which is the same as what we have on our outer secondary. So what we're first going to do is we're going to have a look at the voltage across our inner secondary. This is just open voltage test. All three windings are wound the same way, so of course our waveform on both secondaries is going to be matched. And if you're wondering why it was matched on the primary, it's because I had the scope arse about face, so I have to keep it on our common ground. As you can see here, we are still set on 1 volt per division on each channel, and we know that the yellow trace is our outer secondary of our transformer, and the blue trace is now on our inner secondary of the transformer, and we have 2.56 volts RMS, which is near double what we have on the outer secondary as in an open voltage, even though the wind ratio, or the turn ratio of all three windings are the same. Now the reason we're running at 1 kilohertz, so 1 kilohertz, I'm just running this off our signal generator, 4 volts peak to peak, and the reason I'm running so high is at the lower frequencies this transformer is pretty crap. If we can, I'll drop it down to 100 hertz. And you can see now on channel 1 we have 360 millivolts RMS, channel 2 760, and our RMS voltage from our signal generator is 1.414 volts RMS. So at low frequencies this transformer is pretty crap. It has to be up around the 800 hertz mark before we start to see the good stuff. Now a little thing with the RMS voltage from our signal generator that it's telling us that is 1.414 volts RMS is what it should be at the 4 volt peak to peak, but of course because we have it across the resistor and this is only capable of about or low power output anyway, as far as current goes, our RMS voltage on our secondary is not quite as much as what we put in across the primary. So the primary would actually have less RMS across it due to the fact that this doesn't have enough grunt to overcome the resistance to put out what the RMS voltage of the signal generator is telling us. So it will be a little lower until such time as we get up in frequencies. Then the RMS voltage across both channels is higher than what we are reading from our signal generator. As you can see, channel 2 is saying 2.52 volts RMS, and our signal generator says it should be only 1.41, and channel 1, which is our outer secondary, says 1.24, which is a little lower than what our signal generator is saying. So you can see that the output voltage from our inner secondary, even though it's a 1-to-1 turn ratio and we have a lot less wire on our inner secondary, the open voltage is a lot higher than the outer secondary. This is going to be a relatively long video, so if you want, you go grab your popcorn and that now, or just switch it off and go do something interesting. So we're going to do some load tests on it now, and we're going to do a visual load test first, and we're going to put these two identical LEDs, one in each secondary, which go through two identical full wave bridge rectifiers, and we're going to have a visual look at the output energy from our two secondaries. So remember, this one on the left is our outer secondary, this one on the right is our inner secondary. The other thing I want to show you, this that's not what we wanted. I'm just going to raise the frequency up, and we're going to go up to 10 kilohertz, right about there, and we'll turn our blue channel down 1 division. So now our blue channel is on 2 volts per division, yellow channel is on 1.4 volts RMS on the yellow channel. So we've lifted up 10 kilohertz, and our outer secondary stayed much the same, along with our inner secondary open voltage. So I'll just keep cranking this up. I just wanted to show you a little something which you'll start to see. I'll go to 200. So now you can see our outer secondary at 250 kilohertz, 800 millivolts RMS, whereas our inner secondary now has 5.6 volts RMS, and of course our delivered RMS voltage is 1.41 volts. I'm going to keep going up on the frequency. Now you can start to see a bit of a phase shift taking place here as the frequency rises, and we can get that phase shift to go 180 degrees out at 350 kilohertz, but still the inner secondary RMS voltage is a lot higher, until such time so we're now at 500 kilohertz. The outer secondary has 1.28 volts, the inner secondary has 1.2 volts, so we're starting to shift it around now. And I might just change that over to channel 1 at this point in time. That is our trigger. So we'll go to 1 meg. So the outer secondary is still reasonably stable, and we've pretty much well lost everything on our inner secondary, 200 millivolts RMS, and the value on our outer secondary is 1.4 volts RMS, and our supplied RMS voltage from our signal generator is 1.4 volts RMS. So just a little sweep on the frequency there to shows you what happens. As you can see, we can take them right out of phase by 180 degrees. Oh, sorry about the shaky camera work and getting in the road and all that crap, but anyway, just going to go back down to our 1 kilohertz now. Okay, so we're back to our 1 and 2 volts per division, 1.28 volts RMS and 2.64. So we're getting double the open voltage at the lower frequencies from the inner secondary than what we are on the outer secondary, even though it's a 1-to-1 turn ratio. What we're going to do now is change over. We're going to put our 2 LEDs in and have a little look-see there. Okay, so first up we'll try 1 LED, which is on our outer secondary, and I have the yellow channel across the primary, and our blue channel on the scope is across the AC side of the secondary. and you're looking, and of course the primary is inverted in the way that I've put the scope leads on, keeping my common ground. So of course if we swap them over, they would be as they should be, 180 degrees out of phase. So 2 volts per division on each channel, and at the moment the LED, I don't know if you can see that, is just starting to conduct, and we are pretty much 2.16 volts across our primary coil, 2.16 volts on our secondary coil. So we're going to wind our voltage up a little more. Where are we? Okay, so our primary is now at 3 volts RMS, and our secondary is 2.96 volts RMS, so pretty close, and our LED is shining away quite brightly there. So what I'll do now is I'm going to remove this LED, and well, I can just put this one straight into our secondary hole here for the time being. Yeah, we're going to put the LED in the connection that is of course our inner secondary, and we're going to leave our signal generator as it is, and we will try and keep the 3.04 volts across our primary and see what voltage we have on channel 2, which will be our inner secondary in the next part of the test. At the moment we have 2.96 volts. Notice the brightness of the LED. Okay, so our yellow channel, once again, as you can see, we've rounded the waveforms off. That is because the LED is really conducting now, but you can see our yellow channel is still across our primary as it was. We have roughly the same 2 volts RMS, but we now have 4 volts RMS across our blue channel, and that LED is blindingly bright. It's a 3 volt LED which we've currently got. We're at 2 volts division, and we're putting in over 4 volts across it on both sides of the waveform, minus our voltage loss across the rectifier. We can actually have a look at that. I'll put the scope across the DC output side, polarity correct of course. Now I can't see because the LED's blinded me. Right, so now we're looking at the blue trace is our DC output. We have roughly about 2.8 volts RMS across channel 2, which we can't do. So we'll just have a look at the that is channel 1, that's not the one we wanted. I'll just change that to mean 2.72 volts mean or average across that LED, which is just about its maximum voltage. And of course we've dropped a little in voltage across our primary coil, 0.2 or 0.02 volts, whatever it was before, but not very much. And yet we're getting a whole lot more energy from that inner secondary, as you can clearly see. Alright, so what we're going to do is I'll just stick the LED in and we'll have a look side by side now, and see the comparison between the outer and the inner when the primary is being fed that same amount of power feeding it. Okay, so you're probably not going to believe that, but both LEDs are in now and only one from the inner secondary is going. As you can see, the one across the outer secondary simply doesn't have enough in it. We've got 1.76 volts average across our outer secondary coil, which is not enough after the diodes and everything to make that LED conduct. But while it's up and running, I will remove this LED like so, and you can see now that our LED is indeed lit. Not as bright because we still only have 2.48 volts across that LED. Right, so next part of our test, we're going to stick some resistors in. We'll start with 100 ohms and then we'll just keep adding a resistor and check each one and see how it's going. Alright, so we have a 100 ohm resistor across our outer secondary and a 100 ohm resistor across our inner secondary, and that is what we have. Let's turn those voltage divisions down a bit, get a bit more wave in the screen. 920 volts RMS across our outer secondary and 100 ohm resistor, and we have 1.84 volts RMS across our inner secondary 100 ohm resistor. So what I'll do while it's running, I'll just, so we had 1.84 volts RMS across our inner secondary with that 100 ohm load across it. So I'm just going to remove the load on the outer secondary, and we now have 2.16 volts RMS on our inner secondary across that 100 ohm load. Alright, so the next, just stuck that resistor back in primary coil. So I'm just going to go and chuck another couple of 100 ohm resistors in there to bring our resistance down a bit and increase our load on our two secondaries, and we'll come back and have another look at that. Okay, so now have a 50 ohm load across both the coils, both our secondaries, and I have the we're just going to have a look at the RMS voltage across our primary coil. At the moment is 560 millivolts RMS, and with our 50 ohm load across our inner secondary, which is our blue channel, channel 2, we have 1.04 volts RMS. So even with a 50 ohm load on it, we still have nearly double the voltage across that inner secondary as we do across our primary. I will now put channel 1 back across our outer secondary as such, and you can see the outer secondary RMS voltage with the 50 ohm load is pretty much the same as our primary, but our inner secondary is near double that of the outer secondary, while across the same load. So I'll go ahead and I'll put another 100 ohm resistor in there to bring it down to about a 35 ohm resistance, and we'll have another look. Alright, I've done it the cheats way. I've just used clip leads to hook on our last resistor. Once again, red channel across our primary, or yellow channel should I say. We have 400 millivolts RMS across our primary, 720 millivolts RMS across our secondary with our 33 ohm load across it. I will move our scope back to our primary coil, 360 millivolts RMS, and still the 720 of course. If I disconnect that 100 ohm load, we have 360 millivolts, and makes no difference to the primary hooking that last resistor on, but it does make a difference to the secondary which is interesting. So that's with the last resistor on the primary disconnected. So 360 millivolts with 50 ohms across it, and 760 on our inner secondary. Sorry, that is the outer secondary, not primary. And when I hook the extra resistor up, like so, we still have 360 millivolts across that outer secondary, but our inner secondary dropped down a little. And if I disconnect that extra load on the inner secondary, that goes up to 960 millivolts RMS and 480 on our outer secondary. So there we have our 35 ohms across our primary, outer secondary and inner secondary. Sorry, not the primary. And that's pretty much the result. So even though that all three windings are a 1-to-1 ratio, the outer the primary and the outer secondary that's wound on with it are pretty much very close to one another all throughout the load tests, but the inner secondary always has nearly double the voltage across the same load, even though the turn ratio is identical to the other two windings on the outside. There you go, interesting stuff. I'm going to print that one off and remove that, so we now have our 50 ohm load as before, and I'll print that one off too to post on the forums. And that's about it for this video, because the battery's nearly flat, so it's going to take a long time to sort out and get uploaded, and a long time for you guys to watch it, but interesting little setup indeed. Thanks for watching, guys.